Are you in the basement? Looks like you're in the basement.
I'm totally in the basement.
Oh my god. Okay, so I just got back from Guatemala, and I discovered some people there who were talking about stuff that I'd never heard of before. At first I thought I just spoke Spanish really badly, which was true and remains true, although it's gotten better. But actually, I think that what they were talking about was real.
So I was coming to my house. I was actually preparing myself to go to bed, and I was closing my eyes, and then the earthquake started. I thought that I was like sick, because everything started to move for me, and I said, "Wait, am I okay, or what is happening?" Right? So I woke up from bed, and I went out from my room, and I had some backpacks on a higher place, and one of them fall down on me. And it was really scary. It was one of the scariest moments in my life, because my family started to scream. I went outside. I was looking at the sky, because right in front of my house I can see the Santa Maria volcano. So I can see the mountains around the city. So I started to see some lights, like an aurora boreal. So I thought that the cable electricities were like falling down, and I thought, well, we're going to have fire here. But then when I saw a little bit better, they were lights that were going out from the mountains, and those lights are like the colors are like greens with yellow, and it's, well, now I can say it is awesome, because it's something natural. But at the moment I said, well, I'm gonna die here. The city is going to be destroyed, and I'm gonna die. My name is Edward. I'm from Guatemala. I'm 26 years old. We are located in Cielo, Guatemala. It's the second biggest city in Guatemala. There's no place like Cielo. I have lived here in Cielo for my whole life, and I do not remember saw this kind of lights before. We were talking the day after the earthquake, and we were talking about that some of the people on the city saw the same lights that I saw. And I thought they weren't going to believe what I was telling them, but it was something crazy.
So I didn't meet anybody from Shayla who had pictures or recordings, but I did talk to a number of people, and they were like, "Oh yeah, I saw them," or my boyfriend saw them, or "Oh yeah. Talk to this guy, he saw them." But during the same earthquake in Mexico City, a number of people were filming.
Oh, cool.
And so I sent you some links to some videos there.
Whoa. Whoa. Oh, it's like lightning, but there's no arcs. It's just lighting up. It's like it's just casting on the clouds like huge flashes. They only last a second, That's so cool. What the heck? Alright, that's ridiculous. Whoa. I'm all done.
Coming at you from the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh peoples, this is Future Ecologies, where we explore the shape of our world through ecology, design, and sound. I'm Adam.
And I'm Mendel.
And what you just heard was Mendel reacting to videos taken in Mexico City during the September 9th, 2017 earthquake that struck off the Pacific coast of southern Mexico and Guatemala.
Yeah, it was pretty intense. 8.2 on the Richter scale.
And the videos seem to show what Eduardo earlier described as aurora borealis-like lights occurring in brief flashes over the city.
Well, in this video, it looks like some thunders from the clouds, but it is pretty similar.
Obviously, the aurora borealis is restricted to polar regions, and so this is something else entirely.
Yeah, Cielo, Guatemala is not exactly in the Arctic.
And it was in Cielo that Eduardo and several other people drew my attention to this phenomena.
And it's those interactions that Adam had that sent us way, way down this rabbit hole into the world of earthquake lights and other unexplained earthquake-associated phenomena.
Which, as a scientific field, is more like a minefield. The videos, which you should definitely watch online, are prime fodder for conspiracy theories, which you quickly run into. We thought we were looking into this very specific, very strange phenomena, but the box we opened up turned out to contain centuries worth of unexplained sightings, the science, or pseudoscience, depending on who you ask, of earthquake prediction, and the state of our earthquake early warning systems here in North America.
So with no further ado, let's start with what you found out about the history of these so-called earthquake lights.
Yeah, so there's documentation of earthquake-associated lights going all the way back to the 1600s BC. These can be anything from the northern lights kind of lights that Eduardo described to floating orbs in the sky or fire-like flickery light coming out of the ground. A great recent paper collects 68 of the most convincing and best documented of the literally hundreds of sightings from the last few hundred years, together in one place. And some of the witness accounts are pretty wild. Check this one out, from February 5th, 1663. After an earthquake in Quebec.
We saw fires, torches, and flaming globes which sometimes fell to the earth and sometimes dissolved in the air.
And here's another, from May 21st, 1874. An earthquake near Asheville, North Carolina.
A strange phenomenon of lights was witnessed by many, lights which frequently shot up from the mountain. A few nights before Thursday evening's shocks, a party of 4 or 5 at Spicer Springs saw a huge light moving up Broad River, which shone with such intensity as to exhibit the trees and hills for an eighth of a mile on each side of the river, as if it were daylight. It shone but 5 minutes, and disappearing, left all in darkness.
And we should stop right here and say that, like any and all mysterious lights that people claim to see in the sky, earthquake lights have had their skeptics from day one.
More recently, though, after a series of photos taken in Japan during the 1965 Nagano earthquakes, many scientists have come to accept that there is, at the very least, something worth looking into here.
But again, there is still no consensus that what we're looking at here is a coherent, distinct phenomenon and not a collection of misguided observations.
So there's your disclaimer. I'm kind of inclined to believe the folks I spoke to in Cielo, and there are actually a surprising number of articles online, many in reputable publications, that reference these phenomena. And many of them point back to this one guy.
Yeah, my name is Friedemann Freund. I am originally from Germany. I was professor on geoscience in Germany for 15 years, and chemistry also. And then I moved here to America because when I came as a NRC senior fellow to NASA Ames Research Center, I liked the place so much. And I did like also the climate here in Northern California.
Dr. Freund is at the center of much of the research and controversy surrounding earthquake lights. I met him at the SETI Institute,
That's short for the Search for Extraterrestrial Intelligence.
which, of course, is located in an unassuming office park in Silicon Valley. I found Friedman pretty fascinating, but I'm going to turn it over to Mendel at this point, because, honestly, the physics here is a little bit out of my league.
Well, I'm no rock physicist, but I'll try to break it down.
In a segment that we're going to call Mendel Explains a Thing.
So Freund's interest in this field began with his PhD thesis.
I choose at that time, that was way back in the 1970s, I choose to work on a kind of crystal that everybody says it's so boring. Everything is known about this crystal.
Which is magnesium oxide.
Isn't magnesium oxide like the thing that you light on fire in Chemistry 101?
I think that's metallic magnesium.
Oh, yeah, like just magnesium.
Just magnesium, yeah.
Before it's bonded to oxygen.
Yeah, that's the pure metal form.
Because I totally remember lighting it on fire with oxygen, actually, right?
Mm-hmm.
But I found some very strange anomalies in this crystal. And within a few years, I had discovered that actually I had found a new type of structural defect on the atomic scale in these supposedly super high purity, very simple crystal structures. And I sunk my teeth into this.
And he still has teeth.
Huh.
He actually has quite a charming smile.
Cute. So after becoming fascinated by the molecular defects in this seemingly simple crystal, Friedman discovered that the same defect was present in a whole class of minerals known as silicates. These minerals comprise over 90% of the Earth's crust. At the molecular level, they're composed mostly of silicon and oxygen. The defect that Friedman discovered is called a peroxy bond. It's a kind of imperfection that forms in the crystal structure when the mineral first cooled from molten rock. Normally, where there would be a single oxygen with a charge of -2, there's a pair of oxygen ions, each with a charge of -1.
Doesn't a negative charge mean that an atom has, like extra electrons, right?
Exactly. Oxygen is at its happiest, or rather, its most stable, when it picks up 2 extra electrons from what it would normally have as your standard oxygen atom. But when these rocks form, 2 oxygens can occasionally get locked in this quasi-stable peroxy bond. Under normal conditions, it doesn't make much difference. Silicate minerals don't usually conduct electricity. That is until...
I did one experiment that everybody to whom I told I would do it said I'm absolutely crazy. I took a long piece of rock and stressed it only at one end, and then I found the electricity arriving at the other unstressed end. When I stress a rock, the rock, which is normally an insulator, becomes electrically conductive.
Wait. I'm sorry.
No, that's okay.
I just have to stop right here.
Yeah.
He puts like some strain on a rock and electricity flows through it?
That's exactly what's happening.
Where's it coming from?
So Freund's theory is that when the rock is squeezed, those peroxy bonds actually break from the stress, and they steal an electron from a neighboring oxygen. The donor oxygen is now suddenly free to move around in the rock matrix, hunting for a replacement electron. And you can think of this ion, what we call a particle with a charge, as a roving absence of an electron. And it's known in the world of semiconductors as a hole, a positive charge that travels through a material.
So it's a thing, but the thing that it is a lack of a thing.
Yeah.
Right? It's like an absence.
Exactly.
It's a space.
Exactly. Yeah, it's a hole. It's a place where an electron can hop into, and then where that electron came from is another hole, so that hole can keep traveling.
Right. So the electrons are moving kind of one direction, and the hole is moving the other direction.
Basically.
Isn't that like a battery?
It's a lot like a battery. And Freund is saying that in this model, the Earth becomes a battery.
Whoa.
These charge carriers can flow out, and they propagate. We measure their propagation speed. They travel with about 100 meters per second, which is about, well, the speed with which an airliner lands on an airport. More importantly, they spread over tens and even hundreds of kilometers. They spread out over a large area. And now these charge carriers are all positive. So the ground, which is essentially an insulator, is now laced with positive charge carriers that are mobile, and they all go towards the surface of the Earth.
The surface of the Earth. That's where we live. They're heading for us.
They're coming for us.
So what happens when they get there?
We'll get to that, but let's take a little break first.
We're gonna go eat some rocks. Okay, so I'm gonna recap to see if I understand this. When the rocks that form the bulk of the Earth's crust are squeezed, they can become semiconductors, generating a flow of positive charges that we call holes.
Mm-hmm.
And then the positive charges flow up to the surface of the Earth. So how do we get from that to lights coming out of the tops of mountains?
Because these charge carriers repel each other, they end up preferentially on the topographic heights. So suddenly you get an accumulation of these charges on the peak of the mountains and the hills, and that's where they can achieve charge carrier densities enough to ionize the air or even cause coronal discharges.
Coronal discharge is also what happens when you drink too much beer. Oh my god, that's the perfect term for this. Way better than Aurora Borealis like.
Yeah.
So that's the link between the charge carriers and the earthquake lights.
Mm-hmm.
But how and why do the charges build up in the ground? Like, what would cause that?
That's a pure physics because of the dielectric constant. The rock has, let's say, a dielectric constant of, let's say, about 10 or so. Air has a dielectric constant of 1, and that is just a trap. The boundary is a trap for any mobile charges.
The dielectric constant represents how much electrical energy a material can store in the form of an electric field. So he's basically saying that there's a natural boundary right at the interface between the air and the ground.
I'm so glad that you just interjected because I did not know what he was talking about.
And then they actually start to ionize the air. That means air molecules, and it's preferentially oxygen, that are touching the surface become so torn apart that they lose one of their electrons to the ground.
So as these charges accumulate, the electric field at ground levels builds up to 10 million volts per square centimeter. That electric field accelerates nearby electrons to the point where they can rip apart the molecules of the air, a process called ionization. When this happens, the light of a corona discharge is produced.
That's wild. I have kind of a party pooper question here.
Go for it.
Which is, I mean, I don't know that much about batteries, but to have a battery, you need to be able to complete a circuit, right?
Right. So
like, it's not just a one-way flow.
Mm-hmm.
And I'm curious about how Freund explains that.
So, hand waving, that is pretty complicated according to Friedemann and Freund, and is definitely one of the more controversial parts to this theory. How is this process repeatable? How do the p-holes regenerate inside of the rock matrix?
I guess this is where you would refer to the literature.
Yeah, I refer you to the literature.
Wouldn't there be other effects if we really did have all of this charge buildup at the ground air interface?
So yeah, this flow of electrical charge could be responsible for all sorts of other phenomena. Well, of course, there's also water in the Earth's crust. This water is in form of little films, film water, intergranular water. That is actually a very good conductor of these charge carriers. But in the moment you have a body of water, the dielectric constant of water is 81. And at this boundary between ground, doesn't have to be solid rock, it can be also mud, and water, such a high electric field is building up that you electrolyze the water, and water becomes stoichiometrically oxidized to hydrogen peroxide.
Nobody likes to swim in hydrogen peroxide. Even I know that.
Well, it's of course a tiny amount of peroxide, but normal water, seawater, groundwater, always also has dissolved organic material just from nature. And this organic material becomes oxidized. And there is, for instance, one process that I'm very actively interested in, namely, could it be that this oxidation of the organic molecules that are dissolved in regular water can lead to new compounds, and we know they can lead to new compounds, but if these compounds are neuron toxin, we would suddenly start to understand why millions of fish die in shallow water before earthquakes.
But this isn't just a problem for fish.
From a chemist perspective, these electronic charge carriers that I was mentioning that have the capability of propagating, they are actually extremely highly oxidizing, highly aggressive radicals.
So are these free radicals? These are the same free radicals that we're always worried about and why we eat lots of blueberries and buy antioxidant things. Is that right?
That's right. It's actually probably also the reason that fireflies glow, but we'll get into that another time.
And they probably cause, for instance, for animals that live in moist environment, they irritate the skin and make them want to leave their environment because they cannot stand it. It becomes intolerable.
I find that when Fern talks about animal behavior, it can sound a little bit far out, but I want to relate to you this really interesting research paper from 2009. So you ready?
I'm ready.
Okay, so these two researchers, Rachel Grant and Tim Halliday, they're studying bufo, which is essentially the common European toad. And they've been studying this toad for years in the same place, these lakes in this area called L'Aquila, which is kind of in the center of the Italian boot, right?
Okay.
And they're studying them during the breeding season, when the male frogs arrive and they get ready to, get down.
The action is high.
Yeah, exactly. And if you've ever been near a pond where toads are breeding, you know that it's raunchy.
Yeah.
Yeah. And that when they are breeding, not much can disturb them, right? Once they're engaged,
difficult to distract.
Yeah, exactly.
I know the feeling.
Yeah, it's understandable. And so what was really fascinating about this study in this particular year is that, of course, they didn't know that an earthquake was going to happen. About a week before this earthquake happens, most of the frogs disappear.
That's not normal.
No. They had just arrived, ready to breed, and then suddenly, poof, they're gone.
Party's over.
The researchers have no idea what's going on. They're literally, running around looking for frogs, trying to figure out where the hell they went. And there's an earthquake. And then after the earthquake, the frogs start to return. And they start to set up for breeding again. But it kind of disrupts their breeding cycle this particular year. So they don't return in the same numbers either. And so it looks like they, quite clearly
sensed an earthquake.
Sensed that there was an earthquake happening, right? The researchers go through and they try to figure out if anything else could have happened.
Mm-hmm.
And since then, Rachel Grant has done a number of different papers, one from Peru, several with Dr. Freund, actually, about how these pee holes could possibly affect the water and cause these frogs to leave.
Right. I think it was basically that it changes the chemistry of the water in a way that makes it physically uncomfortable for them to be in the pond. So they're just I'm getting out of here.
So yeah, and that's one hypothesis. There's also other ones, like radon gas and infrared and ionization of the air. So nobody knows quite what's going on here. But what's interesting is that finally, after essentially centuries of these just anecdotal evidence of animals reacting preemptively to earthquakes in weird ways, we're starting to get, just in the middle of a study about something completely different, when all the animals disappear and then an earthquake happens, we're starting to get some traction. So something must be changing in the crust of the earth. But we don't hear about an earthquake until it's actually happening.
Nope. If we do get any warning, it's because the P wave has hit seismographs before the destructive S wave arrives. When it comes to estimating when an earthquake is going to arrive, we mostly just hope that earthquakes on a given fault are reasonably periodic. That's just to say that we hope they happen on fairly regular intervals.
Yeah, hope is kind of a strange word for that.
Yeah. Well, it makes them understandable, which
Right.
is what we want.
So when people say we're overdue for the big one up here in the Pacific Northwest, that's essentially what they're saying, is that we think there's a periodicity here.
Yeah, that's been about 500 years, and they usually happen every 500 years, so it's about time.
So that kind of periodicity might help us know, say, whether an earthquake is going to happen like this decade or in the next 20 years or something like that. But that isn't really helpful for our day-to-day lives, except as like kind of a low grinding anxiety.
Yeah, earthquake kits in all the elementary schools.
So the question that hits my mind is this work that Friedman has been doing. If his theories are correct, couldn't they offer us an ability to predict earthquakes before they happen?
That's exactly the dream.
From my perspective, talking about earthquake forecast, I don't use the word prediction, but I use the word forecast, and that's the same goal that the seismologists have. They would like to forecast when a big disaster happens, but they cannot, because the Earth does not reliably produce mechanical precursors. But to everything I know, the Earth produces absolutely reliably electrical precursors. So we should focus on the electrical precursors.
So conventional seismology sort of treats earthquakes from just a purely mechanical perspective. What they're trying to do is they're trying to model the stresses that the crust endures and measure how it moves when it finally fractures.
Not an easy job.
No, that's putting it lightly. The instruments that they use are called seismometers, and they're really just devices that are very, very sensitive to motion. So some groups are trying to see just how far we can push this understanding to protect lives and infrastructure.
So what is earthquake early warning, and how is it different from other warning systems? So many people are familiar with tornado warning systems or hurricane warning systems, where they see a storm developing somewhere and then they say, ooh, it's going along this pathway and it's going to impact you. So, hey, heads up, this thing's coming your way. So earthquake early warning is pretty much the same thing. We see an earthquake starting somewhere and we say, hey, the earthquake is coming your way. It's just that for hurricanes, you get a couple days notice. Tornadoes, you might get half-hour notice. Earthquakes, you might get a second or two. So the earthquake has already begun. So it is not earthquake prediction. This is earthquake early warning that an earthquake has started, and we're sending info your way.
That's Dr. Jennifer Strauss, who I got to speak to at UC Berkeley.
Yeah, so my name is Dr. Jennifer Strauss. I'm the External Relations Officer for the Berkeley Seismological Laboratory.
Dr. Strauss is also a regional coordinator for Shake Alert.
So Shake Alert is a consortia between the United States Geological Survey, universities along the West Coast, so Caltech, here at UC Berkeley, U Oregon, and U Washington, that are all working together to try to bring earthquake early warning to the United States.
So Shake Alert is working with utilities, transportation groups, and healthcare facilities to develop procedures for what is likely to be a very brief early warning. And it's worth noting that the US and Canada are kind of late to the party when it comes to earthquake early warning systems.
We haven't had a massive earthquake that has killed massive numbers of people like Mexico and Japan have. And so their countries really had to address an egregious problem quickly. They also were focusing on a problem that happens offshore. And so very large subduction zone earthquakes that happen offshore can produce massive amounts of shaking, impact people really far away from the earthquake. In that sense, you kind of have a little bit of time from when the earthquake starts and when it really starts shaking your heavy population centers. In California, we have the problem where people like to live where really pretty landscapes are, and that was created kind of because of all our earthquakes that we have here. So you're putting your people on top of the problem. And when you do that, you don't really have a lot of time between when the earthquake happens and when you need to warn people. And so you kind of had to wait for stuff to be able to be fast enough to provide that sort of warning. And that's where we are now.
So with a few seconds to spare, trains can be held in their stations, surgeons can put down their scalpels, and the word can go out to drop, cover, and hold on. Shake Alert is upgrading and linking together existing seismic networks along the Pacific coast and refining the algorithms that notice an earthquake in the making.
And in order to make the most out of their quake identifying algorithms, Shake Alert has the ambition to build a global seismic network using your smartphone. Their app, called MyShake, is built to be your portal for earthquake notifications and a way to crowdsource data from millions of accelerometers, those extremely sensitive little devices that you have inside of your cell phone that tell it whether it's facing up or down so the screen knows which way to flip.
If you're using your phone during the day, MyShake doesn't care. That's just human activities. For its purposes, that's very boring, so it ignores it. But then after you've set your phone down for a bit, it's like, ooh, something might happen. So it listens to the accelerometer, and it waits and it listens. And it's got an artificial neural network on board that decides, with the data coming in, whether the thing that is recording is an earthquake or is it a human activity. And the human activity stuff, again, it doesn't care. It ignores it. But if it's an earthquake, then it starts recording. And it saves that information. And number one, it sends a trigger message to our cloud server that, aha, I think that there's an earthquake. And if other phones nearby you say, aha, we also think this is an earthquake, then we can aggregate that information and say, aha, there was an earthquake there.
So I just love citizen science projects like this. I think it's amazing that an app can turn your average cell phone into an earthquake sensor.
And there's lots of earthquake sensors in California, but in places like Nepal, where there are really frequent and damaging earthquakes, having all of those portable cell phone sensors out there is literally the difference between having absolutely no data or warning and maybe having some warning.
Yeah, and maybe having enough. That said, I'm still fascinated by Frun's vision of using electrical precursors to get a little bit more warning. I know I'm not the only one, so I head down to Palo Alto after the break.
And this is California Avenue. We're now arriving at the California Avenue station cut.
This is QuakeFinder. Since 2000, they've been listening to the electrical signals from the Earth, and they've been trying to tease out how they correspond to seismic activity.
And unlike Shake Alert, which is a consortium of the U.S. Geological Survey and a number of universities, QuakeFinder is a private venture, supported almost entirely by their parent company, a satellite and aerospace engineering consultancy called Stellar Solutions. You literally could not get more Silicon Valley than this.
They even have some contributions by Elon Musk and Pacific Gas and Electric.
Or PG&E, for us Californians in the room.
Tom Blyer, CTO of QuakeFinder, gave me a tour of their headquarters and the equipment they use to hunt for earthquake precursors. Tom actually first got interested in the subject for the same reason we did, earthquake lights. I've got to say sorry in advance for the noise in this interview. The AC was on high and my microphone skills were on low.
Are we recording now? Or
We are, if that's okay.
Okay, yeah.
Here's Tom introducing the first instrument in their arsenal, the magnetometer.
Think of it as a bar of metal that is highly conductive to magnetic fields. So it actually acts like a funnel. It funnels these signals through and then goes out. But wrapped around the bar are tens of thousands of windings of electric wire. And anytime you change the magnetic field over a coil of wire, it generates a voltage. So a small amount of magnetic field change over thousands of turns of wire, it's like an amplifier. It amplifies it.
Let me see if I have this straight. Magnetometers sense the changes in the Earth's magnetic field caused by a flow of current that's theorized by Dr. Frun?
That's right. Yeah, that's exactly it. These things are sensitive to picoteslas, which means they also pick up all sorts of human electronic noise.
Ooh. So there's probably tons of that in the Bay Area, right? Like it's probably the noisiest place on Earth for human electronic noise.
Yep.
What other sort of signals are muddying the magnetic waters?
It can see currents in the electronics, so Everything is a noise source. We could take our cell phone and just sweep it across there and you'd see a huge signal because there's tiny currents going on in the cell phone.
Not only can it pick up readings from its own electronic components, it's sensing nearby cell phones or even someone walking by with a set of keys in their pocket. But one noise source stands out above them all: Bay Area Rapid Transit.
Oh, I know that one.
Every time a BART train starts up, it creates a huge magnetic pulse, and we can see that for 10 miles. Even though we put our sensor on the other side of the hill behind Berkeley, the ultra-low frequency goes right through that hill like there was nothing there.
You might be wondering if they can also monitor the BART trains and use that to cancel out the junk data.
Oh, like noise-canceling headphones. I know technical stuff.
We actually tried that. We put magnetometers right next to the track when they started. Early Sunday morning when the BART system starts a little bit later. But we found out quickly that there were other trains starting on the other side of the bay even before we put our magnetometers down, and they broadcast through the 140 miles of track like a giant antenna.
This sounds like a total pain in the butt.
Yeah, I mean, that's really all just to say that you're not going to get clean electromagnetic data in a busy urban area.
One that just so happens also to be built directly on top of a major fault line.
So luckily, QuakeFinder has another tool in their data mining shed: ion sensors.
Ooh, what's an ion sensor?
So this is an ion sensor. Little black box about the size of a brick of cheese. There's a chamber in the bottom part with a plate through the middle of it. So if you can imagine a stream of air being sucked through this with a little fan, if the air is dry like it is in this lab right now, there will be no current going between that plate and the outside edge. If there is ions in the air, it'll start creating a current between the plate, and we measure the amount of current, and the higher the current, the more density the ions are.
So when an electric field from the ground starts ionizing the air, these sensors are measuring those charged particles directly? Are they as sensitive to human activity as the magnetometers are?
No, in fact, QuakeFinder is collecting data from their ion sensors up and down the Hayward Fault, which happens to run right alongside the BART tracks. But the final piece of data collecting machinery is by far the coolest. I mean, literally, it's it's in space.
So luckily there's a satellite above California called the NASA GOES weather satellite. And that satellite at geosynchronous orbit is staring down at California, and it can pick up this long wave infrared, and it looks like the area is heating up at nighttime, which is very strange.
In my experience, the ground tends to get cooler after the sun goes down. So, what's happening here?
It's an illusion. The ground isn't actually getting any warmer or colder than usual. When something is hot, it's actually glowing in the infrared spectrum. But infrared light can also be generated when ions in the air eventually get neutralized. So this GOES weather satellite interprets light from deionization as aberrant warming on the Earth's surface when it's really just happening in the air.
Okay. So if the satellite says, hey, the ground is getting hot, but it's nighttime, then there's potentially some ion action going on somewhere down there, either on the surface or in the atmosphere. So there's the magnetometers, the ion sensors, and the infrared detectors on a weather satellite. What are they actually seeing with all these data? Can they detect earthquakes?
According to QuakeFinder, yes. After eliminating as much of the noise as possible, they compare all their data to the seismometers. Leading up to an earthquake, they see a characteristic pattern of activity. About 2 weeks before the quake, there are lots of pops on the magnetometers, more than 10 times the normal rate for several days. Then, mysteriously, everything gets quiet. The day before the earthquake, the pulses return, and the ionization readings go through the roof.
Amazing. So there's like a fingerprint, if I can call it that an earthquake might be about to happen. And that I mean, if I'm doing my math right, that's more than a week of warning. So how much information about the quake can they get from that data?
Well, that's the disappointing news. QuakeFinder doesn't want to make any claim that they are currently able to predict earthquakes. Right now, they can't actually say for sure if there's a connection between the size of the signal and the magnitude of the quake.
Ah, yeah. Well, that's science.
Yeah, and the exact timing and location are also not a sure thing yet. We don't really know how the charges may have moved through the rock or how the ions may have moved through the air, so it makes it really tricky to say exactly what's about to happen.
So, QuakeFinder is willing to put money on the idea that there are detectable precursor signals before earthquakes, electrical signals. But we don't know yet if those precursors are actually useful. A big earthquake announcement, taken seriously, could lead to some very expensive precautions, or at worst, a panic.
In practice, it's all about certainty. What is the chance that that signal is a false positive? QuakeFinder currently has a confidence in their signals of about 2.5 to 3 sigma, which means that about 1 in every 220 forecasts would be nothing.
Is that good enough? Like, do they expect to be able to get more precise? What is a sigma anyway?
A sigma is a statistical measure of the standard deviation. So it's basically saying there's so many standard deviations away from a chance event.
I see. Okay.
Yeah. So in particle physics, they would call that evidence, but not a discovery. To claim a discovery, you have to have 5 sigma, which is closer to 1 in a million chance that something is chance.
Right.
Something is a random event rather than not. At this point, it's more of a math and statistics exercise than anything else. They're sitting on 80 terabytes of raw data from over 170 detectors around the planet. They're recording more than 1,000 earthquakes larger than 2.5 magnitude. The trick is to get the signal out of all that noise.
That is a lot of data. Yeah, they're gonna have to eke out whether there's a way to forecast the really important stuff, like how big the quake is and when and where it will arrive.
Exactly.
Somewhere in the data.
But we're living in the age of big data, and it's possible that the tools to solve this problem are finally mature. QuakeFinder has just joined forces with a machine learning group.
Which machine learning group?
Sorry, for the time being, that's confidential.
Ah, I see.
But if everything goes well, they hope to have some results to announce by the fall of 2018.
You tease. So does that mean it's just a waiting game? Can they make any use of their detectors right now?
It will be a while before we do public forecasting, at least in the United States. To do the socially responsible thing, you need to be really good at it before you start emptying out cities, ahead of an earthquake. So what is that, number? If you look historically at hurricanes and tornadoes and the weather, at the point where you're about half right is the point where you're doing more societal good than societal harm. Now, that's not to say that there aren't private forecast organizations, for instance, that have large distributed infrastructure.
That's Dan Coughlin. He's QuakeFinder's former director of research and development, and now serving as an advisor to the project.
His analogy to hurricane prediction is pretty interesting. I mean, hurricane forecasting essentially went from no warning to 1 day of warning to 3 days of warning. It's only really since 2001 that reliable 5-day warnings have been possible. So maybe the only way to get there with earthquakes is just to keep looking for those patterns. Maybe we'll get there with MyShake, or Shake Alert, or maybe we'll get there with Froon's theories and QuakeFinder.
Or maybe the Earth is just more noisy and complicated than we have the time, or the money, or the ingenuity to decipher.
I think this is a good time to mention how difficult it was to engage the seismic community on Froon's research. Essentially, we contacted researchers up and down the west coast of North America, and many of them kind of punted us to other researchers.
Yeah, claiming that they didn't know enough about it or they hadn't heard of it, which seemed odd for people who are supposed to be experts in the subject matter.
Right, and those who would talk to us would only talk to us on background. And essentially, the message that we got was Froon's theories and his work are solid enough to be taken seriously, but that nobody really wants to engage with them because at this point, they're pretty hard to test. And people don't really want to go on the record either way as saying like, oh, this is like totally bogus. And then, maybe they're wrong later.
Yeah.
Or, kind of prematurely being like, yeah, let's go with this. And then maybe it turns out that there was nothing there.
It's true. And the few people that are vocal about it are in just strong criticism of each other. Both sides think that the experiments that the other is running are completely invalid for one reason or another. So it's hard to see the truth. But overall, what was really surprising was just the deafening silence in the literature, that there wasn't really any ongoing discussion about is this right or is this wrong? Here's why. It's just, here's a theory, and the establishment is more or less ignoring it.
Right. The deafening silence in the American literature.
That's true.
Right. I mean, what's interesting is seeing different researchers in Japan, in Peru, in Europe, in New Zealand, taking Froon's ideas and starting to apply them to their own research and to things they've observed in earthquakes around the world. It's really just here in North America that people have been real quiet. Which, I mean, Froon will definitely insist if you ask him that, essentially like the seismological establishment kind of wants to silence his ideas. He's pretty convinced of that.
I think in human interaction, particularly in the academic world, there are two ways to react to something with which you disagree. You can either counterattack and publish something that say, oh, he's wrong and that cannot be true, or just silence. Just silence. And behind the scene, I do have evidence that people are interfering even at the government, at the NASA headquarter level, to cut my funding.
It seems easy for them to see his work as just another theory, another fringe theory in a long line of fringe theories. There's been people who've claimed to be able to predict earthquakes before, to obviously no results.
Like if you have something really cool, like I'm all for cool, like I kind of want to see it. But 4 photos of, some lights you saw the last time you were in an earthquake is interesting, and it adds to this body of lore or more background data that maybe somebody will pull through later to do a study. But you got to have legit stuff. It can't be just a fly-by-night theory. The reason why a lot of the scientific community is a little jaded about this stuff is because some of it is very apocryphal, some of it is very anecdotal, and we get a lot of emails from people who are like, I have this really cool model that I really need somebody like powerful and with lots of money to help me, prove that this is my earthquake prediction thing.
Maybe ego takes over from good science, that people want to stake a claim of their discovery over what is actually legitimate data. So they see these theories as being just an expensive distraction, and they don't actually want to draw any more attention to it. So they would rather just keep on the path.
Right.
Yeah.
And along that line, it's also worth noting that the other thing that a lot of these researchers explain to us is that for several decades, like from the 60s onward, the seismological community spent a lot of resources trying to find mechanical precursors to earthquakes.
Mm-hmm.
They spent a lot of time trying to figure out how you could predict them. And essentially, after decades, many of these same researchers that we're talking to now came to the conclusion that it was a bit of a dead end, that we wouldn't be able to do it.
That's mechanical precursors, not electrical precursors.
Right. Well, and most seismologists they're studied in the mechanics of these things. I mean, it takes somebody who's interdisciplinary to be able to look at both the electrical and the mechanical and kind of understand. It's very complicated stuff. But I think there might be a little bit in there of like, we tried to find something that could help us predict earthquakes, and we spent a lot of resources, and we couldn't do it. And now you're telling us that like we weren't looking in the right place, right? And maybe we're just like, we don't want to go through that same experience again.
So the perspective from the flip side is a common refrain in our history. Silos of belief that proclaim to be subject to logic and evidence, but stay closed to discussions that threaten to change their model of the world.
Which is essentially, like, this is how science advances, right? Like, it doesn't advance in a linear fashion. There will be kind of like a theory, and it will hold, and it will hold, and even if it's wrong, it will hold as evidence accumulates until there's just so much evidence
That it fractures.
yeah, that there's a fracture. And that's referred to as punctuated equilibrium, which is a cool ecological concept. It's essentially the idea that things will, instead of changing gradually, or an evolution instead of diverging gradually, there will be these sudden tectonic shifts in our understanding. It might take a new generation of folks, like the folks at Quakefinder, willing to crunch the numbers and really establish the monitoring facilities and check this out.
Yeah, if Quakefinder or any other hopeful earthquake forecaster does eventually put out a warning that can't be ignored, or they publish a data set that convincingly relates a reliable precursor to earthquakes, then we're really going to see a tectonic shift in how people think about geoscience. But until then, keep an eye out
For lights in the sky.
These lights is a good memory for me now. At the moment it was scary, but at this time for me is a good memory. I don't think I'm gonna forgive these lights in a short time, but I just want to say let's try to keep the nature, to protect the nature, and obviously enjoy the nature. It's the only planet that we have. We are destructing the planet, and it's not fair for the animals, for the plants, and neither for us.
Thanks for listening. We'll be back in a couple of weeks. Please tell everybody that you know. Subscribe, rate, and review the show wherever podcasts can be found. It really helps us get the word out.
In this episode, you heard Edward Gonzalez Godinez, Friedemann Freund, Jennifer Strauss, Tom Blyer, and Dan Coughlin.
This has been an independent production of Future Ecologies. Our first season is supported in part by the Vancouver Foundation. If you'd like to help us make the show, you can support us on Patreon. To say thanks, we're releasing exclusive mini-episodes every other week. The first 2 are already out. To get in on the action, go to patreon.com/futureecologies.
You can also follow us on Facebook, Instagram, and iNaturalist. The handle is always Future Ecologies.
Special thanks to Riley Byrne at Podigy, Andrzej Kozlowski, Sarah Sachs, and to David Skolsky.
That's my dad.
A lot of research went into this episode. If you want to read the underlying research, we've cited all of our sources in the show notes for this episode. You can find them at our website, futureecologies.net.
Music in this episode was produced by Sunfish Moonlight, Jonathan Shirk, Dr. Turtle, and Radioactive Bishop. Thank you so much for all your help.
And for all of you herpetologists out there who might have noticed that I flipped halfway through my story about Bufo Bufo from saying toads to saying frogs, we acknowledge here at Future Ecologies that toads and frogs are different. Different enough to be in different families. So thank you for noticing.